Hi everyone, I'm your friend Shadab Imam and we are continuing our lecture series on operations research. If you are new to the channel, please subscribe the channel and don't forget to hit the bell icon. So today I came here with a very interesting topic, that is degeneracy in linear programming. So let us understand what degeneracy is. Degeneracy is basically a state in a problem where after iteration our objective function does not improve. Okay, so it is basically a state in a problem where after iteration our objective function does not improve. We'll see how it happens. So now let us understand where actually degeneracy occurs. So degeneracy occurs when one or more basic variables has a zero value. We know that in the variables in the basis column are known as basic variables. That means if the value of these basic variables is 0, then our problem is said to be degenerate, and the degeneracy can occur at any stage of the problem. That means the degeneracy can occur at the initial stage, in the initial basic feasible solution, or at the subsequent iterations. So let us see how it has happened. At the initial stage, the degeneracy occurs when at least one basic variable is 0. That means in the initial basic feasible solution, that is in the first matrix, if at least one of the basic variables will have a 0 value, then our solution is said to be degenerate. It can be understood that when the right hand side value of the constraint is 0. So basically it happens that in our constraint equation the right hand side value is given as 0. So in that particular type of problem we can see that at least one of the basic variable will have 0 value. That means in that problem our problem is degenerate. And degeneracy can also happen at the subsequent iteration. That means after basic feasible it can be either first iteration, second iteration. So in that what happens is there is a tie among the minimum non-negative replacement ratio. Okay, so now what is minimum non-negative replacement ratio? It is the value of theta that we calculate. As we see in the subsequent iterations, if there is a tie for a leaving variable, then we can say that our problem is degenerate. What actually happens is whenever there is a tie between the leaving variable, we can select any of the variables arbitrary, and what happens in the next stage is the other variable will attain the value 0. So ultimately the value of one of the basic variables becomes 0 and our problem is degenerate. And in degeneracy the value of z, that is value of our objective function, does not improve. It is also interesting to see that what degeneracy reveals is that the problem has at least one redundant constraint. So what is redundant constraint? We have done one problem in the graphical method where one of our constraint was redundant constraint. Redundant constraint is nothing but when a constraint does not contributing to the feasible region. That means if we remove that particular constraint, we do not have any change in our feasible region or in the value of objective function. That particular constraint can be called as redundant constraint. We'll see here also that what actually redundant constraint is, and many a times it has been seen that after the problem has become a degenerate, the iterations are continuously repeating. That means they are giving a locally optimal value rather than maximum value or minimum value which is desirable. So that particular case is known as cycling, and cycling is a very rare phenomena in degeneracy, but it may happen sometimes. Now let us understand how degeneracy works with a problem. Problem says that maximize z is equals to 3x1 plus 9x2, 3x1 plus 9x2, okay, subject to constraints x1 plus 4x2, subject to constraints x1 plus 4x2 less than equal to 8, less than equals to 8, and x1 plus 2x2 and x1 plus 2x2 less than equals to 4, and x1 comma x2 greater than equal to 0. Now, in order to solve this problem, first we need to see the first we need to convert this problem into standard form, and we need to see that the right hand side value of the constraint has non-negative. So as we see that 4 and 8 are non-negative, so we can move ahead. So we are converting this equation into standard form, which is maximize z is equals to 3x1 plus 9x2 subject to constraints x1 plus 4x2. This is less than equal to 8, that means we'll add a slack variable here. This is equal to 8. Similarly, x1 plus 2x2 plus another slack variable s2 equals to 4. Then x1 comma x2 comma s1 comma s2 is greater than equal to 0. Now let us quickly make our first matrix. Okay, this will be plus 0 s1 plus 0 s2, as it has 0 contribution to the objective function. Now let us make the first initial basic feasible solution. x1 x2 s1 s2, these are our decision variables with objective function coefficient 3, 9, 0, 0. Now to make the initial basic feasible solution, we need to have the value of x1 and x2 equal to 0. So as we put x1 equal to 0 and x2 equal to 0, I'll get s1 is equals to 8. That implies that s1 is eligible to enter the basis column. Similarly, in the second constraint, if x1 and x2 are 0, s2 is coming as 4, which indicates that s2 is eligible to enter the basis column. So we have s1 and s2 with objective function as 0 and 0. Now the constraint equation 1, 4, 1, 0 equal to 8. This will be 1, 2, 0, 1 equal to 4. Okay. Now let us calculate the value of Cj minus Zj. So as we can see that Cj is 3, minus of Zj is this multiplied by this plus this multiplied by this. So 3 minus of 0 is 3, this will be 3. This will be 9 minus 0 is 9, this is 0 and 0, and the value of Z here is also 0. Now we will select the maximum value in the Cj minus Zj column. So this will be our key column. That means variable x2 will enter the basis column, and we need to find the leaving variable. We need to calculate the value of theta, which is right hand side value divided by corresponding key column element. So right hand side value is 8, corresponding key column value is 4. 8 by 4 is 2, okay, 8 by 4 is 2. Similarly, right hand side value is 4, 4 divided by 2 is 2. So now as we can see here, that there is a tie between the two leaving variables. So let us arbitrarily select any of the two variables. So right now I am selecting this variable, and this row will become pivot row. That means variable x2 will enter the basis and it will replace variable s1. Okay, so let us, x2 will replace s1, so this will be x2, this is s2, variable x2 is 9, this is 0. Okay, and I need to make this is our pivot element. We need to make this as 1 and the remaining values in the column as 0, so this has to be 0. In order to do that, what I'll do is I'll divide the first row by 4. So this will be 1 by 4, this is 1, this is 1 by 4, this is 0, this is 2. And we need to make this element as 0. So what I'll do is row 2 minus of 2 times of new row 1. Okay, row 2 minus of 2 times of new row 1. So this will be 1 minus of 2 times, that means into 2, this will be 1 by 2. So this minus this will be 1 by 2. Okay, and this will be 0. This minus this will be minus 1 by 2. This is 1 minus 2 times of this will be 1. This minus 2 times of this, 4 minus 2 into 2, 4 minus 4 is 0. So now, as we have discussed about degeneracy, that it may occur initially when any of the right hand side value of the constraint is 0, or in the subsequent iteration when there is a tie between the two leaving variables. So here is the tie between the two leaving variables, and we have selected this as the outgoing variable s1. As a result of this, the other variable will attain the value 0 in the next matrix. Okay, so it is clear by here now. Now let us move on and solve. So again I'll be calculating the value of Cj minus Zj. This will be 3 minus 9 by 4. 3 minus 9 by 4 will give me answer as this is 3 by 4. 3 minus 9 by 4 will be given me 3 by 4. Then this is forming unity matrix, so I'll be writing directly 0 because they are the basic variables. And this is 9 by 4, so this will be minus 9 by 4, and the value of z is coming as 18. Now here we can see that all the values in the Cj minus Zj row are not 0 or negative. There is one positive value here, so we will select this value as key column, and now this will be our entering variable. This variable x1 will enter the basis, and to select the leaving variable we will see that it is right hand side value divided by corresponding key column element. So 2 divided by 1 by 4 is 4 into 2 8, and 0 divided by 1 by 2, anything divided by 0 is 0. And one thing we need to remember here, that the value 0 is treated as minimum positive value. Okay, clear? We need to understand that the value of infinity or negative value we do not calculate here, but the value of 0 is taken as minimum positive value, so we will select this value, because among these two this is minimum, so we will select this as pivot row, and this shows that variable s2 will be the outgoing variable. Now let us move on with the matrix. This will be x2, and now s2 is replaced by x1, so this will be 9, this will be 3, and we need to make this as 1 and the remaining values in the column as 0. So what I'll do is I'll multiply the row 2 by 2. So this will be 1, 0, minus 1, 2, 0 into 2 is 0. Similarly here I can see that row 1 minus of 1 by 4 times row new row 2. Okay, so this will be 0, this will be 1, this will be this row minus 1 by 4 times of this row, this will be 1 by 2, this is 1 by 2, this is 1 by 2. Similarly this is minus 1 by 2, and this is coming as 2 minus 0 is 2. Okay, now to check the optimality we will again calculate Cj minus Zj. So as x1 and x2 are basic variables, I am directly writing here the value 0, because x1 and x2 are basic variables and they will have the value 0 in the Cj minus Zj column. Now we'll calculate this and we'll have minus 3 by 2 and again this is minus 3 by 2. So and the value of z is coming as 18. Now we can see that all the values in the Cj minus Zj row is either 0 or negative, so we have our optimal solution here, and we can see that because there is degeneracy in the first iteration, we have the same value of z in the subsequent iteration. We have the value of z as 18 here, and the same value of z we find here. That means after doing an iteration the value of z does not improve. Clear? So what degeneracy does is it increases the number of iterations. Clear? Now let us understand that what had happened if we have selected initially this as the outgoing variable. In our first matrix we have selected this as the outgoing variable, we have selected it arbitrarily, and now let us understand that if we had selected this, what had happened. In order to see, let me erase this, let me erase these values so that we can analyze it. So let us see here what had happened if we have selected. So now let us select this as our leaving variable. So I am selecting this as pivot row. Now as we can see here that variable x2 will enter the basis and it will replace the variable s2. Okay, so let us write here variable s1 variable x2. So x2 has replaced variable s2. This is 0, this is 9. Now what we need to do here is, now this will not be our pivot element. Our pivot element will be this now. So I have to make this as 1 and the remaining values in the column as 0. So I'll be dividing this equation, that means row 2 by 2. I'll be getting 1 by 2, 1, 0, 1 by 2 and 2. Similarly, to make this as 0, I'll do row 1 minus of 4 times new row 2, so that this will be 0. So this minus 4 times this will be 2, 1 minus 2 is minus 1. This will be minus 1, this will be 0, this will be 1, this will be 0 minus into 4, that means 2, this will be minus 2. Okay, this will be 8 minus 4 times of this is 0. So again we can see that now again after the tie we have one of the variables, basic variables, having the value 0. Now we will again calculate for optimality if this solution is optimal or not. So we can see that 3 minus 9 by 2, it will give as minus 3 by 2, and these are the two basic variables x2 and s1. So the value of Cj minus Zj is 0, and this will again be minus 9 by 2, this will be 18. Now as we seen here, now that all the values in the Cj minus Zj row are either 0 or negative, that means our solution here is optimal and the value of Z is coming as 18. So in selecting both the variables, we have seen that selecting variable s2 as the leaving variable initially is more fruitful or less laborious than to select the variable s1 as our leaving variable. But the problem arises that how do we know or how do we select our leaving variable? So in the general method it has been said that you can select arbitrary any of the values among the tied variable, but there is one method which is known as perturbation method. Okay, there is one method known as perturbation method, which gives us a sequence or a procedure to select the variable whenever there is a tie on the minimum non-negative ratio. Okay, so what are the steps? Let us understand. So first step is to divide each element in the tied row by positive coefficient of the key column in that particular row. So let us see what this means is, we need to divide each element in the tied row. So among these two tied row, each element in the tied row by the positive coefficient of the corresponding key column. So let us suppose this is the key column. So I'll be dividing each of these elements by corresponding value of key column element. That means this will be 1 by 2, this will be 0 by 2, this will be 1 by 2, because the corresponding key column element is 2. Similarly here we have corresponding key column element here is 4, so this will be 1 by 4, this will be 1 by 4, this will be 0. Now the second step is to compare the ratios starting from first identity matrix, then the body matrix. As we have known here that the two matrices here are, first this is your identity matrix which shows the basic variables, okay, and the next is your body matrix. So once we have calculated the ratios, we need to see first the identity matrix and then the body matrix. So let us see here and compare the values, and as soon as we got the least value or the smaller value, we will be selecting that particular row as the leaving variable. So let us see. For this variable, this is our first column of the identity matrix, and the value here is the value of algebraic ratio here is 1 divided by 4, because 4 is the key column element. So this will be 1 by 4. I am writing here, this will be 1 by 4, and the subsequent value is 0. So this will be 0 divided by 2. 0 divided by 2 is 0. So as we can see that the two values we are getting at first is 1 by 4 and 0, and 0 is the minimum positive value present here. So what we will do is we will select the value 0, that means we will select this as our leaving variable. Okay, now if in case there is a tie here, suppose there it is a 3 cross 3 matrix, then we will have 1 0 0 0 1 0 0 0 1. In that case there may be a tie here. So what we'll do is we'll move on to the next column in the identity matrix, and even if there is a tie, then we will move towards the body matrix from left to right. Clear? So it has been clear that according to perturbation method, what we have done here is we have divided each element in the tied row by the positive coefficient of key column element in that particular row. So for this we have done 1 by 4, 1 by 4, 0 by 4. Similarly here 1 by 2, 0 by 2, 1 by 2, because 2 is the key column element here and 4 is the key column element here. And we had compared starting from identity matrix. So for the first column in the identity matrix, we have seen that this value, the ratio for this value is 1 divided by 4, where the ratio of this value is 0 divided by 2, and the ratio is coming as 1 by 4 comma 2, or I should say 1 by 4 or 2, and among these two 0 is the least positive value. So I will select the value 0 and we will select this S2 as our leaving variable. Okay, clear? So now friends, let us see another aspect of this question. Recently we have talked about the redundant constraints. So to understand the redundant constraint, we need to solve this particular problem through graphical method. So let us start solving this problem. To solve this problem, we need to convert these inequalities into equations and make sure that the right hand side value of the constraints are non-negative. So I'll be writing the equations here. That means maximize z is equals to 3x1 plus 9x2 subject to constraints. That means x1 plus 4x2 equal to 8 and x1 plus 2x2 equal to 4, x1 comma x2 greater than equal to 0. Now let us draw the constraints now. If I put x1 equal to 0, I'll get x2 equal to 2. That means I'll get this point. That means 0 comma 2 is the first point I got. Similarly, if I'll put x2 equal to 0, I'll get x1 equals to 8. So this will be 8 comma 0. Okay, please consider this as the straight line, and the equation says that there is a less than equal to sign. That means the feasible region is towards the origin. Feasible region is towards the origin, and for the second constraint, if I'll put x1 equal to 0, I'll get x2 equal to 4 by 2, that means 2. I'll get the same point here 0 comma 2, and if I'll put x2 equal to 0, I'll get x1 equal to 4. So this is the new point I got, which is 4 comma 0, and I need to join these two points, and now we can see that the feasible region is towards the origin because the sign here is less than equal to sign. Now in this problem, the feasible region following both the constraint is given by this area. Okay. Now as per the problem, there are two constraints, but if you analyze the graphical view of this particular problem, you can easily understand that there is one constraint which is x1 plus 4x2 less than equals to 8. Now if I remove this constraint completely from the problem, there will not be any effect on the feasible region or on our objective function. Okay, so we can say that this particular constraint or constraint with this equation x1 plus 4x2 less than equal to 8, this constraint is a redundant constraint as it is not contributing towards the feasible region, and if we remove this constraint, there will not be any effect in the feasible region or on our objective function coefficient. Now to calculate the value of z, we can calculate it at corners A, O and B. Suppose I'll be calculating z at A, z at B and z at O. I'll be getting the values as at A the value is 0 comma 2, that means I'll put 0, x1 equal to 0 and x2 equal to 2. I'll be getting the value as 18. Similarly, if I put ZB, that means 4 comma 0, x1 equal to 4 and x2 equal to 0, I'll be getting 4 into 3, 12 plus 0. So this will be 12, and at 0, x1 equal to 0, x2 equal to 0, I'll be getting z as 0. So we can say that at point A, the value of z is maximum. This is our z max, and this is what we have also seen in this simplex table. Okay, we are getting the value of z max as 18, we are getting the values of x2 is equals to 2 and x1 does not appear, that means the value of x1 is equals to 0. But the problem arises when we have more than two variables. When we have more than 2 or 3 variables, then we could not solve the problem graphically, and by solving the problems through simplex method, we could not surely say that which of the constraint is a redundant constraint. So the degeneracy, it is clear with the degeneracy that as degeneracy occur, at least one of the constraints is redundant constraint, but by solving through simplex method, it is very difficult to say which one of the constraint is a redundant constraint. Okay, so I hope you like the lecture. If you like the lecture, please subscribe and share the lecture. Have a nice day. Thank you.